Recording.
Good morning, good afternoon, good evening to everybody. I have the pleasure to present the first speaker of this conference, a colleague and also a friend, Enrique Zuazua. Enrique Zuazua is professor at the University of Erlangen-Nuremberg in Germany and the Universidad Autónoma de Madrid in Spain, and also holds the chair of computational mathematics at Universidad Deusto in the Basque Country in Spain. He is a very well-known researcher in applied mathematics, covering topics such as partial differential equations, system control, and application. He has supervised important amounts of PhD students and postdoctoral researchers, and recently he has explored with success connections of control theory and machine learning techniques. Among others, he has been awarded the Basque Country Prize in Science and Technology in 2006 and the Spanish National Prize 2007 in Mathematics. He is also a member of the Scientific Council in several international research institutions, and member of the editorial board in some of the leading divisions in applied mathematics and control theory. Today, he is going to give a talk on control and machine learning. So you can start, Enrique, as you want.
Thank you, Enrique. So first of all, I would like to thank the organizing team, and especially Juan Límaco, as Sandra, I think, has said, our master, el maestro, ¿no? Maestro, ya era maestro Juan Límaco antes y desde 2020 que ha mantenido esta dinámica de manera estable y constante, pues nos ha unido a todos nosotros. So I'm very pleased to be here for celebrating these 4 years of this event that Juan has been organizing in a very professional way, and that has allowed us to be all together in these sometimes difficult times. I mean, some other occasions like now, being far away, but able to be together. So as Enrique has said, in the last few years, mainly when I came to Erlangen in September 2019, I observed that a lot of the interest of the university, in particular the computer science faculty and the engineering school, and also some colleagues in mathematics, was oriented towards machine learning, artificial intelligence. And then I thought that maybe this was a topic that we could also explore from our, say, previous background in analysis of PDEs, numerical analysis, traditional applied mathematics. And then, as Enrique has said, it's a topic that we have tried to develop in the last 4 or 5 years, in particular from this perspective of control theory. And I would like to give you a brief overview of what we have done and where we stand. This is a lecture I have given already a number of times, but I try to make it evolve so that I can share with you where we stand. So first of all, the context, I think, is very clear. So artificial intelligence, we like it or not, we know more or less about it, is nowadays part of our daily life. So you see to the right the logo of ChatGPT. I don't need to explain you. I mean, you can just, there are other large language models. You can install it in your iPhone for free, and you can ask all kind of things, including, I don't know, something that I did recently. For instance, tell me about the state of the art of the finite element approximation of the spectrum of the Laplacian, for instance. And then you will get immediately, plenty of bullets with relevant information, also some references. What was a bit a surprise for me is that I even got a reference of a paper that I could not find. So it was a paper that it actually doesn't exist. The authors being Ernst and Letalek. So Ernst and Letalek certainly have written papers on that topic, but not a paper with that title. And that was a surprise for me to see that ChatGPT was able to give a reference of a paper that then going to Google Scholar and Mathsinet, I could not find. So, but on the other hand, when you look to the, to the meaning of the acronym ChatGPT, G is for generative, P is for pre-trained transformers. So generative pre-trained transformers, meaning that ChatGPT is able to generate, and therefore in this aim of generating, it can even provide you information that actually doesn't exist, like fake mathematical references. So it's a tool that now is at our disposal. We use it all the time, but we have to do it cautiously. On the other hand, so this is on a daily basis somehow, right? So you can use ChatGPT for translating text, for improving text, for generating images, for generating LaTeX files, for checking LaTeX files, for so many things. On the other hand, the most relevant technological applications are nowadays also employing more and more tools arising in machine learning, also predictive control, which is really very close. Reinforcement learning and model predictive control are two topics that are very, very close. And this is being used in order to enhance the existing computational and applied mathematics techniques by learning from data. And this is an article, for instance, that recently appeared in by the Institute of Natural Sciences. I think I found that in the news, right? So we have every few months we see articles of this kind, magnificent application somehow combining classical mathematics and machine learning. In this case, in order to generate digital twins for fusion plasma. So we see that these kind of tools related to machine learning and artificial intelligence are now present in our scientific activity at the very, very different scales, right? From simply correcting a letter to, tackling very challenging applications. And then, so in this talk, which will be quite, light, a dissemination talk, I will say, I would like to briefly explain you how I understand things are occurring. So maybe the first thing to explain is how does it work? What is the computational practice of machine learning? So a big difference with the main difference probably with classical applied mathematics is that in machine learning, we don't have models, right? So we have just data. So what we do is, in order to very much inspired in the classical ideas of Gauss for linear regression, we build a large nonlinear model, which is kind of a graph as plotted there. So it's a neural network, but it's just a graph where many nodes, neurons are interconnected through different coefficients that are introducing weights to the different neurons. And what is very relevant in machine learning and artificial intelligence, in these neural network architectures, there is always a nonlinearity that is playing a fundamental role. So in contrast with classical linear regression by Gauss, right? Least squares. Here we are adopting nonlinear models in order to be able to better approximate nonlinear manifolds of data. Okay, and then what we do is we say, listen, I have some data, a data set. Related to this data set, I also have some labels. And what I'm trying to do is try to simply identify what are the best coefficients in all these neurons so that the output of this nonlinear graph will be as close as possible as to the data I have, and this I do it by just minimizing a nonlinear function in which I try to minimize the distance of all of them simultaneously to the corresponding targets. Of course, in order to do this, and because we need some coercivity, we will also penalize the coefficients by adding some classical regularization terms like, in Tikhonov regularization. So in this way, you find a problem which is finite dimensional. So you can simply claim that using classical tools of the calculus of variation, you can guarantee the existence of the minimizer. And this is something also you can implement in the computer easily and get in this way a model that is more or less taking care of the data information you have provided. Now, when you look closer to, what is the complexity of the models under consideration, I recommend you, for instance, this web by 3 Blue, 1 Brown, that is disseminating videos in order to better explain the architecture and the mathematics of ChatGPT. You see, for instance, that in the free version of ChatGPT, ChatGPT 3, that we can all download for free, the number of parameters in this model is of the order of 175 billion parameters. So there are 20 times more parameters in ChatGPT-3 than humans on planet Earth. So indeed, the dimension of the problem is finite, but is huge. Therefore, we face immediately the course of dimensionality as Bellman-Kuhn coined in the context of control theory when he developed, the classical Hamilton-Jacobi-Bellman equations for the principle of dynamic programming. So you see that on one hand, even though the problem is formulated in discrete terms and everything seems to be finite dimensional and continuous, the dimension is huge. And on the other hand, of course, because of the nonlinearity of the model we have adopted in this nonlinear graph, combining nonlinearly neural networks, right, neurons, the model, the functional we have to minimize is extremely non-convex. So there are two difficulties we have to master. One is the course of dimensionality, and the other one is the devil of non-convexity. Despite of this works. Why does it work? Well, one of the reasons for this is the fact that there are theorems, the so-called universal approximation theorems. This paper by Sivenko is one of those that is more quoted in this area. By the way, you see that this paper by Sivenko, published in '89, was published in a journal, Math Control Signals and Systems, devoted to control theory, right? So at that time, therefore, it was clear there was an intimate relation between, control theory and this emerging new field. So in that paper, what Sivenko says is that, listen, this class of functions is also dense. We know polynomials are dense. This is Stone-Weierstrass. We know Fourier series are dense. We know that finite elements can also approximate all kinds of functions. These are classical results. Well, there is here a new class of functions that is also able to assure this density, the universal approximation property. But the main difference of this approximation procedure with respect to other more classical ones is that this is a nonlinear approximation procedure. Why? Because in order to build the finite dimensional ansatz based on which we will guarantee the density, we employ a nonlinear activation function, this kind of sigmoid function, like the profile of a traveling wave. And then, other than, of course, taking a finite number, capital N, of neurons sufficiently large, because as usual in approximation theory, a parameter has to tend to infinity in order to guarantee this universal approximation. This is the parameter capital N. Even when you fix a priori capital N, large but finite, you still have to find the coefficients alpha, y, and theta, and you see that y and theta enter nonlinearly in the activation function, the sigmoid function sigma, okay? And then the proof of Sivenko, which is very beautiful and is based on Ham-Banach theorem, says, listen, if you take a sigmoid function like this class of functions is dense in the space, say, of continuous functions or LP functions locally in space, okay? And the proof, as I said, is not very difficult. Now, is this result the unique one and isolated? Not at all. So there are plenty of results of this form. Actually, there are earlier results by Norbert Wiener, the so-called Tauberian theorems, that guarantee similar things, but for, say, activation functions that instead of having this sigmoid profile have the profile of a Gaussian. You can see this sigmoid as a primitive of this Gaussian. And there are other functions that, like the rectified linear unit, which are even simpler geometrically, flat at the origin, 0 to the left, and then linear to the right, which are being more employed nowadays simply because they are somehow of a more elementary geometric nature. Okay, now as I said, this works. So this methodology works because there is the theorem of universal approximation that guarantees that every function you might have in mind, in particular the function that can be representing the data you are observing in any kind of natural or industrial process like meteorology or people behavior, right, or language, structures. You can, by this theorem of density, approximate by this very elementary neural network ansatz as the one that Sidenko developed. Okay, but now when you see the level of success of the modern large language models, you still think, well, it's true, there is density, and maybe density is a sufficient argument to guarantee that we should be able to, but in practice, it works so well that we wonder whether there is not something else behind. And in fact, there is nowadays a lot of mathematical activity, more or less coming from all areas of mathematics, in order to try to explain why these methodologies are working so well. What we did was to somehow, inspired on our previous know-how in control theory, try also to contribute to explain this incredible success. So here I have taken a video in which I present you two simulations, one simulation on the left. This is a paper that was published in the journal M3AS that Nicola Berromo is running with Franco Brecci. I have seen Nicola among us some minutes ago. So on the left, you see a classical control application in which 4 dogs in blue are herding a flock of sheep in red. So in that case, this is a classical, say, application of control for animal behavior. We have a system of differential equations, which is coupling the dynamics of sheep with the dynamics of dogs, and we apply classical control theory techniques in order to compute optimal controls that will steer the crowd of sheep to the corresponding destination. On the right, by the contrary, we see the dynamics of a deep neural network that, as you can observe in the final plot of the dynamics, is able to classify properly a data set, splitting it into 3 classes according to the labels, which in this case are the 3 colors, yellow, green, and purple. So if I have shown you these 2 simulations, maybe you could even have believed that the right-hand side was also a simulation on the control on animal behavior. Maybe the question would have been then, well, but if the video on the right-hand side is animal behavior, maybe there are three different classes of animals, right, behaving differently, but where are the controls? We don't see the controls. The controls here on the left are clearly the 4 blue dogs evolving. Where are the controls here? Our perspective to this topic is to observe that even though here we didn't plot the controls are there, are precisely these parameters of the neural network that we need to train or to optimize. And precisely what I'm trying to show you today is that if you employ control theory, you can better understand why these parameters exist and why they can be found as it happens in practice. So, but of course, in order to bridge control theory and neural networks, we need a model. So what is the model? The simplest model you can think of is this neural differential equation, which is a differential equation that for which the state xt is simply tracking the data of your model, which are evolving in a finite dimensional Euclidean space. Every datum becomes a dot in the Euclidean space, which evolves from the initial configuration to the corresponding finite label. And the sigmoid, the function we consider here, just to simplify the presentation, is the ReLU. rectify linear unit, which is a very nice global ellipsis function. So this differential equation is well posed. And because we are adopting the perspective of time continuous, the parameters W, A, and B that were discrete in the previous neural network modeling now become time-dependent parameters. These will be the control parameters. So the main difference of this control problem with respect to others one we are used to deal with in physics and engineering or sociology or biology is that here the model is not inspired on the principles of mechanics, but is simply based in an artificial manner employing this very simple nonlinearity Redd loop. Okay? So now this differential equation is nothing but the time continuous version of this time discrete deep neural network in which instead of piling up as down here, as Sibenko was doing, piling up all the neurons in one shot instantaneously, which makes things hard to be understood from a geometric and dynamic perspective. What we do, we add one neuron in each time iteration in order to build a time discrete version of this neural differential equation. Now, maybe the biggest difference of other than this lack of inspiration in classical or continuum mechanics of the neural differential equation perspective to machine learning is that in this case, we will not do as in classical control theory, where you give me an initial configuration and a target, and then whenever you change the initial configuration and the target, you are allowed to change the control in order to send a rocket, say, from Earth to the moon or back. But rather, in this case, we will need to compute coefficients W, A, and B that guarantee that all the data set simultaneously is being driven from the initial position to the corresponding targets. So we will be automatically dealing with problems that can be considered within the class of simultaneous or ensemble control problems. So this is probably the unique two important differences of this classical control theory and the modern perspective of machine learning. One is the fact that there is no mechanics. You simply adopt this artificial model because, as you will see, it's easy to handle and sufficient to solve the problems we have to deal with. And the second one is that we are not dealing with classical control problems where every trajectory can be controlled by a different control, but actually all trajectories have to be controlled simultaneously. So, okay, this works. I will tell you more in a few minutes. But before getting into it, I wanted just to make a few comments of, we as applied mathematicians, what can we do in this field? And actually, there are many different things we can do, right? And sometimes in the talks that are delivered about, machine learning and partial differential equations in particular, you see different topics being mixed up. And I think it's good to classify them in some sense. So this list here is not exhaustive at all, but these are the three items I would like to discuss here briefly with you. So the first one is very much related to the initial discussion is, why does it work? And then we, as applied mathematicians, from our know-how on whatever field, right? So maybe modeling of complex dynamics or partial differential equations or finite element theory or control theory, we can try to contribute to explain why machine learning is working so well. The second question, which is very different, is how do we use neural networks for classical problems like, for instance, the numerical approximation of partial differential equations? I will mention that a little bit later, but I already anticipate that the price you will pay automatically as soon as you quit classical, say, finite difference or finite element methods is that you will have to confront systematically the devil of non-convexity because it's intrinsic to the ansatz of neural networks, as I have mentioned before, okay? And a third topic, also different, but extremely interesting as well, and which is related to the emerging technology of digital twins that can be, defined as the science where data mathematics, models, and decisions collide. I think this definition was taken from the recent report of the American Academy of Sciences of the state of the art on the state of the art of digital twins. So the third topic, and this is also something different, related, but different from the previous two, is how we can enrich our modeling methodologies by learning from data, and in particular by integrating tools of machine learning, as was anticipated in the first slide I have shown you on digital twins for energy for plasma. Okay, good. So let me go back then to the first question very briefly. So how we can use the maths we know, in particular in this case control, in order to explain the success of machine learning. So, and the first thing to do is, well, how do I bring a problem about data classification into the context of, say, differential equations and control theory? Well, the way to do it is illustrated in this simple picture, in which I have taken 32 items, 32 trash items of different classes. We all understand the problem: plastic, glass, paper, and organic. And then we need to build a machine that is able to classify trash automatically. Of course, this is something we can do, but we don't want to do it very long, right? So we don't want to spend time, classifying trash. We want to build a robot that will be able to do it. And then the robot has to understand what is plastic, and then the instruction that plastic has to go to yellow, what is glass that has to go to green, and so on. So how do we do that? We take each of these items. We can take a picture with our, telephone. Then this becomes just a sequence of pixels. This means that every picture becomes a point in a Euclidean space of very high dimension, because images live in spaces of very high dimensions. And then for every item, we are then indicating what is the corresponding target, and the target can be, for instance, the 4 polar coordinates, right? So it can be north for plastic, south for glass, east for paper, and west for organic, for instance, on the plane. So we have to build a map from a high-dimensional Euclidean space into a space of 2 dimensions that will be able to map these 32 items into the corresponding baskets. So the goal, of course, is not to do it with these 32, but the idea is that if this is the training set, if the training set is rich enough and represents sufficiently well all the possible, say, items that one can encounter when classifying trash, right? Once we do, this function is built so that successfully classify these items, then this function can be used to generalize, right? So that whenever you give me a new item, I will just simply take this nonlinear function applied to this item and see where this function is driving me, hoping that the generalization is correctly done and the item is taken, put into the corresponding correct basket. So you see, we have to build a robot, but in order to build a robot, the first thing we have to do is to be able to build this mathematical function. And then, as I said before, what Sivenko said, the universal approximation theorem says, is, well, if you are looking for a mathematical function, then you can do it according to this ansatz of neural networks. What we have done here is to show you that actually you can also, instead of employing this static ansatz, use rather this differential equation, this neural differential equation. Why neural? Because, as I said, it's purely artificial, and the nonlinearity is adopted a priori as being the one given by the rectified linear unit. We have solved the optimization problem associated to the classification task, the supervised learning task, and we have seen computationally that it works, okay? Now, what is the theory behind? Well, the theory behind, we explain it in this paper, appeared last year in SIAM Review in collaboration with Dominic Ruiz-Vallet, who is now a postdoc in Imperial College. And in that paper, we explain how, actually it's harder to write than to explain why it works. And the theorem says, yes, this can be done. So in Euclidean space dimensions higher than 2, not in one dimension, because in one dimension, there is no room in order to classify data. If you try to move data, they will collide. But if you are in 2D or higher, there is room for data to move freely without collisions of the corresponding items, particles, or trajectories, right? In any finite dimension higher than 2, in any time horizon, you give me any number of data n, and you tell me a priori what are the labels in also a finite number of classes m, we can always find coefficients a, w, and b, depending on time, which are piecewise constant and with a finite number of jumps, so that the corresponding neural differential equation is able to simultaneously control all this data to the corresponding baskets. So not only this function, this robot that is needed in order to classify the training set can be found, but in fact, it can be found as the Poincaré map, as the map, mapping initial data into the terminal values of the corresponding trajectories, if we compute the controls, the parameters properly according to an algorithm or just by training it using optimization techniques. Okay, so here a second comment I wanted to make. Of course, this is related to transport, optimal transport, or generative neural transport, in the sense that once you have built this differential equation, you can view the vector field of this differential equation, which of course is time dependent, is non-autonomous, also as being the vector field of a transport equation that is transporting initial data to destination. So you see that we are being able to transport according to these ansatz. If we choose properly this neural vector field by using these control theoretical ideas, we are able to transport say multi-atomic measure into the corresponding destination. Okay, so this is
Your audio, Professor.
the audio is on. Maybe the link of the internet is not sufficiently good. Can you hear me now? ¿Me oyes ahora?
Sí.
Yes.
Sí, okay. So here now what we do is we don't impose the condition of optimality on the transport map, but by the contrary, we have the advantage that the transport vector field is extremely simple geometrically, because it's simply this ReLU function that is tuned along time according to the parameters W, A, and B. Okay? And the proof of this theorem in the paper by Domenech with Domenech Ruiz-Ballet is very much inspired on the Rubik cube. We all know what solving the Rubik cube means. So this is a disordered Rubik cube, and this is an order configuration, a solved configuration of the Rubik cube. We see that solving a Rubik cube means that every microphase has to be taken to a big phase so that phases are homogeneous. So all the yellows are on one side, all the blues are on the other, and so on. This means that we have classified all these microphases according to their colors in the corresponding baskets. Baskets are now represented by the corresponding phases. And therefore, how we do that for the Rubik cube? Well, in the Rubik cube, what we do is we iterate again and again and again, as many times as needed in order to bring the cube to the order configuration. And in order to do that, in every time step, what we do is we hold with one hand part of the cube fixed, while the other one rotates in the proper direction. Okay, and this is precisely what this neural differential equation allows us to do. Why? Well, because of the very peculiar properties of the nonlinear activation function sigma, the ReLU in this case. Why? Let us simply analyze this briefly. So please keep in mind that xt is simply representing the position in the Euclidean space of this plastic bottle that is moving from the original configuration, like in a Disney movie, right? From the original configuration to the corresponding basket of plastic items, okay? So when we fix time and we observe where the particle x is in the Euclidean space, and we try to determine in which direction it's moving, we see immediately that there are two possibilities. Either this quantity here is negative, and if it is negative, the quantity inside sigma is zero because ReLU is zero to the left, and then this particle is frozen, is not moving. Or by the contrary, this quantity here, this linear combination here is positive, and then sigma is the linear function, and therefore this is a linear ordinary differential equation, which means that this point is evolving exponentially, smoothly in time, according to the values of the corresponding coefficients. Now, what is A and B here? You see, recall, X is a vector in RD, very high dimensional Euclidean space where our data live. Sigma is just a one-dimensional function. So B is just a scalar. So B is just a translation coefficient, okay, that is moving on time. So BT is just a real number evolving on time. AT is a vector that is multiplying scalarly xt. So here we have D controls that are evolving on time. So whenever I take the scalar product A dot x plus b and I look to the interface where the ReLU vanishes, A dot x plus b equals 0, the only thing I'm doing whenever I choose A and B is determining a hyperplane in the space that is cutting the space into two. And we are saying half of the space is frozen while the other one is moving. Well, and what the vector W, now a column vector of d dimensions, is doing is simply telling us what is the direction of motion of the half part of the space that is really in motion. Okay? And now what we do in our paper is to show by a induction algorithm. So here I'm showing you just how to classify one item in 4 steps. We show by an induction algorithm is that wherever the class of initial data is, if you are in dimension 2 or higher, you can build controls in a piecewise constant manner by just cutting a space into two halves and then moving the other strategic one in the proper direction, so that one by one all data are classified. Okay, so of course this theorem doesn't give you the optimal number of controls of switches or jumps that you need in order to solve the problem. This is something that we have further explored with other team members, but it gives you already a very clear idea of how this works and why this works. This works actually because these neural differential equations have this property of ensemble controllability. Okay? Now, concerning the two other topics, very briefly, the first one is neural network approximation of PDEs. This is something we can do, but, and somehow is related to machine learning, but it's a very different topic, right? So then we are not explaining anymore why machine learning works. What we are doing is just taking this idea of Sibenko, of nonlinear approximation theory, and see whether we can develop new computational methods for solving PDEs. So I brought here just an example, like the Laplacian. You all know the Laplacian. We all know the Laplacian is very simple. We have the Lax-Milgram theorem. We have the variational approximation. We have that the solution is the minimum of the energy in the Hilbert space H10. And we know also that based on these ideas, we can do finite elements by simply gamma convergence or Galerkin approximation, by replacing the space H10 by a finite dimensional space of finite elements, right? And then minimizing the same energy in the corresponding restricted finite dimensional space. Finite element theory says if you do that, you get a convergence of order H, at least for domains which are, say, of class C2, so to have good regularity theory. Now, how can you employ machine learning ideas in this context? But you will see this has pros and contras, right? On one hand, it's very easy. The only thing you have to do is to say, well, I replace the ansatz of finite elements by this ansatz of Sibenko. I take k neurons, k being large. In this way, the number of parameters in this ansatz will be k times d plus 2, right? D being the dimension of the Euclidean space where the domain omega is embedded. So there are a a finite number of parameters. But you see that as soon as you do that, now the manifold of solutions of the test functions, the approximation subspace you consider, it will be nonlinear. So you can, of course, still minimize the energy in this nonlinear manifold, and then with some extra effort, because you have the density theorem of Sivenko, you can certainly prove some gamma convergence theorem showing that the minimizers of this reduced finite dimensional problem will converge to the solution of the PDE. But the problem is that even if in this very simple case of a quadratic convex function to be minimized, because you have adopted this ansatz of a nonlinear manifold, the problem here is non-convex, and then you know that finding the minimum is hard to do. You can, of course, apply some stochastic gradient descent and hope you are getting close to the minimizer, but you will never have guarantees as you do have classically in the traditional applied mathematics setting, combining the theory of finite element methods and then conjugate gradient methods, for instance. So you see that you always pay the price of the devil of non-convexity, even when you try to do the simplest possible use of machine learning-like ideas, in this case, just the neural network ansatz in the PDE setting. So what we did rather was to think on how can we tackle the third direction, integrate data into our PDE modeling consideration. So this is, I think, a field that is emerging that I like to call PDE plus D. So PDE for partial differential equations and the last D for data. So how can we enrich PDE with data, PDE plus D? Well, the first thing you can do, this is part of our work in collaboration with Kang Liu, Lorenzo Liberani, and Siqian Li in our team. Now Kang Liu got a position in Dijon, in France. So what we did was the following. We said, well, listen, because we learned how to control data from t equals 0 to t capital T, if you have sensors in a given, say, physical process that are giving you values of solutions at different locations in different times, like initial time, say the black dots, second time, the blue dots, the green, and so on, we can reiterate our procedure of controlling from t equals 0 to capital T. We can do it linking the different time instances in which the sensors are providing relevant information. And of course, we can build a purely artificial model that is able to track this data. This can be done. But then, again, this is purely artificial modeling of data dynamics inspired on the capacity of these neural differential equation models of tracking data. There is no mechanics on it, right? So now, in order to get a bit further, what we did, this is a very elementary observation, but is relevant, is to realize that, for instance, if you are in the context of nonlinear differential equations, if you have a guess, you have an idea of what your model is, and in case the model is non-autonomous, when you employ this kind of neural network approximation methods, you see something very interesting, and is that the approximating differential equation, which might be indeed will be nonlinear because of the presence of the activation function, it will have the very property that the time dependency will be totally trivial, it will be linear. So the model under consideration is not autonomous. This is what we call is semi-autonomous. It depends on time, but it depends trivially on time because it's just a coefficient depending on time. And this allows you to, out of the you all try to anticipate what the future evolution of this data will be, because this is certainly one of the most difficult problems. Not only be able to interpolate the data, but also once we have information about the past dynamic of a system, try to go beyond, right? And then the other application we have explored is how to use this in the context, for instance, of phenomena that are modeled by a transport equation. This is, for instance, a well-known model due to Doswell frontogenesis. This is a paper that is not very well known in the applied math community. It was written in the meteorology community. And it's a model of a transport equation in which you have an explicit solution, right? An explicit solution that you can, this kind of tornado solution that develops this increasingly complex mixed-in rotationary like tornado pattern. And what we have done is to employ these techniques of data-driven modeling of ODEs, right? In order to see that indeed, if you learn from the data on the left, then you can guess what is the vector field in this semi-autonomous manner, and with that, generate the transport equation that is able to mimic Doswell frontogenesis. But in this case, without knowing the PDE a priori, just having the observation on the left on, a finite number of sensors that are tracking the evolution of this fluid mixing. And just to conclude, in order to maybe open up a little bit the discussion, if there is still some time, I think there is still plenty to be done in this area of PDE plus D if we want to further exploit and integrate all we have done in the past in applied mathematics with these new methodologies emerging out of machine learning and data. And I think this could be a good proposal for developing such a methodology, which consists on, on one hand, exploit the possibility that out of data, we can generate models that are purely based in machine learning. Are these, say, neural differential equations that know nothing about mechanics? They simply, employing the very properties of, say, universal approximation in a dynamic manner, these simultaneous and ensemble control properties. They are able to provide artificial models based on neural networks that are able to track data. But on the other hand, whenever we have some mechanical a priori model that we gain because of our experience or modeling, phenomena in dynamics, fluid dynamics or continuum mechanics or whatever discipline it is, then if we have some a priori information, like for instance, knowing that we are in the context of some nonlinear diffusion model, try to gain a hybrid model, generate a hybrid model that will learn both from data and from mechanics by a simple collapse process in which what we try to do is to minimize the gap of these two models. So our proposal for PDE plus D is this hybrid methodology in which we combine classical applied mathematics, but by data-driven model, and then try to find the intermediate model that better interpolates the both of them, right? They will not collapse completely. There will always be a gap, but whenever you minimize this gap or you are getting close to minimizing the gap, you can always claim, well, listen, I have now a new model, which is a mutant, right? Which has learned from mechanics because it originates and is close to the model coming from mechanics, but has also evolved in order to integrate the information coming from data because it has been also built to minimize the distance with respect to this artificial model. And this is a field in which there is plenty to be done. And I hope, I will convince you, at least some of you, that this is a topic that at least deserves some attention, not only for us as researchers, but also, in order to better train the future generations of mathematicians, scientists, and engineers, as we used to do in our universities as a first duty. Thank you again for your attention, for your invitation. Thank you again, Maestro Juan, for all these 4 years of seminars, hoping that there will be many more. Gracias.
Thank you very much. Thank you very much for your talk. We have time now for a couple of questions, so you can write it in the chat or even try to activate the microphone and ask them.
Professor Enrique?
Yeah.
Sí.
In the machine learning community, right, usually one try to generate the the model so it can classify unseen data, right? With these constructions, is there possible that for unseen data, it will be the control that it takes to the target, or it does have any guarantee for this?
You mean the generalization power of all this, right?
Yeah, exactly.
Yeah. So of course we can get estimates for this, right? So once you build a model, because the controls, the coefficients, W, W, A, and B are based on the training data set, if you know a priori some information about the distance, right? In some kind of, Wasserstein distance, for instance, between the training data set and the generalization data set, using the size of the controls and classical estimates, for differential equations of the type of Gromwald, we can give estimates on the generalization power of these models. But of course, these estimates are always very conservative, right? Because after all, we are simply, using control theory to find controls for which we have an a priori bound on how big they are, and then we, quantify the generalization estimates by using the stability properties of these dynamical systems, inequalities like Gromwald that are also very conservative, right? So this is a very good question, and in fact, there is a lot to be done in order to better, sharpen these estimates and try to explain why in practice these methodologies work much better than our very conservative analysis estimates will anticipate, right? And in particular, why these methods are particularly well suited for high dimensional problems, right? Or for data sets that in principle could be huge, right? In which our analysis techniques will provide only very, very rough estimates. And in practice, we see that things can be improved. And then there is several directions of work in this direction in our team in collaboration with our PhD student Antonio Alvarez and some other collaborators. We have two directions of extension of our works that better sharpen our estimates about generalization. One is to exploit high dimension. There is more room in higher space dimensions, and therefore the generalization might be better than expected. And then the second one is that, normally the data sets we consider have clustering properties that allow to reduce the complexity of the control we build, so that this allows to reduce, the estimates on the generalization power. But this is a very difficult topic, even in classical control theory, right? Because after all, optimal controls, those that are really the optimal ones, are characterized either by a Pontryagin maximum principle or by the principle of dynamic programming of Bellman. And I recall you, that's a very good question, actually, the one you formulate, because this allows me to recall that Bellman coined the concept of course of dimensionality precisely in the context of classical control problems. Because he said, listen, for classical control problems, the solution exists, the optimal control exists. It can be characterized as the solution of a Hamilton-Jacobi equation. I think Professor Lyons is lecturing later, right? So he is the one that made the breakthrough to explain why these solutions have a solution, the viscosity solutions. But then what Bellman already anticipated is that even if you have such a nice concept, finding a numerical approximation of this solution will be a diabolic problem, right? And this is when he coined the term of the course of dimensionality. So, we have to remain, calm, be modest, and realize that here we are touching problems of a level of complexity which is even higher to the classical ones in control theory and in the course of dimensionality for Bellman equations, because now we are in a context of high dimensional spaces and large size data sets.
Thank you.
Okay, thank you. We have a last question by Professor Nicola Velomo that had hand.
Well, Thank you for the talk. Very, very well looking forward. I was wondering, you may have problems where different models describe the same systems, maybe, for instance, depending on the observation scale, low or large. And can you think about trying to, the approach can be extended to this type of equations?
Yeah, that's a very natural question, right? So it's, for instance, how do you do multi-scaling here, right? And certainly that's a very, very natural question. So in particular, so here I am working in a given d-dimensional space. I said, okay, I take all items, I take pictures, all belong to the same dimensional space. But in practice, maybe this is not true. We are, dealing with such a diversity of data, so that the different data belong to different dimensional Euclidean spaces.
Yeah.
So
Yeah.
probably then we need to think in terms of multi-scale, right? There are some, there are some topics that are maybe easier to tackle. For instance, there is a very vibrant topic in the context of machine learning is called federated learning. Is when the data set is distributed into different locations and they cannot be communicated. Like, for instance, biomedical applications, when you are combining informations provided by different hospitals, okay? Okay, but these hospitals have information that, because of legal regulations, they cannot simply openly share, okay? So then these problems are very close to domain decompositions, I will say. But what you are mentioning is a step further. It will be federated from the perspective of the multi-scale. This is a very interesting direction. I particularly didn't see anything on this, but you see the literature is so broad that I wouldn't be surprised if someone has already started thinking on this. Yeah, very, very good point, Nicola.
Thank you.
Thank you.
Okay, thank you very much for your talk.
Thank
So we are going to thank you, and we are going to pass to the next speaker. The next speaker is